Mindsetters, welcome to today's Grade 10 Maths Show. Today we have a special revision lesson on functions. We have selected highlights from lessons shown early in the term to help you revise and prepare for your June exams. You can download the notes for today's show from learnextra.co.za/live. Now it's time to get on with today's lesson. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision.
Right, so we've said that relations are a whole lot of x values that are connected to a whole lot of y values according to a specific algebraic rule, okay? If that rule is a linear equation, when we take the x values and y values and we plot them, they're going to make a straight line graph. If the algebraic rule is a hyperbolic rule, it's going to make a hyperbola. All right. Then we said specifically that a function is a special type of relation where the values for x are only ever connected to one value for y. Okay. Now, before the break, we were talking about a vertical line test, and it's just a test to determine if a diagram that's been given to us is a function or not. All right. So let's have a look and see this vertical line test over here. Right, if you're being asked to identify if it's a function, what you need to do is take your ruler and you need to hold it vertically across your graph like I've got over here, all right? And you're going to move your ruler horizontally from left to right along your x-axis like so, all right? And the idea is this, so we go from the lowest x values up to the highest x values. And as we run our ruler across, can you quite clearly see that we are only ever cutting one value for x as the one value for x is only ever connected to one value for y. So basically the ruler is never crossing the graph more than once. And that's the key to your vertical line test, is that as you drag your ruler across the graph, it must only cross the graph once. If that happens, we know that it's a function. So if with regards to this one, is it a function? Yes, it's a function because I know that my ruler only crossed my graph only ever once. Let's apply our vertical line test to this semicircle. As I go across, I can see that this ruler is only ever crossing the graph once at any given point. So is this a function or is it a function or just a relation? It's a function, okay? Let's look at a graph like this, okay? If I take my ruler from left to right and I run it across, let's see, does it cross the graph ever more than once? Okay, it's only crossing the graph at one point, and all the way across you can see that it's never actually crossing it more than once. So once again, this over here would represent a function. All right, we've got one more to try. Let's take our ruler and let's go across. Okay, vertical line test, drag it across. Now, guys, let's watch here. Can you see that at this point, if I draw a line through it, the graph is crossing over there and it's crossing over there, which means that it's passing, the ruler is passing through a graph at 2 points. And because it's passing through 2 points, it means that particular x value was actually related to two y values, meaning that it is not a function. So in that case, your answer would be not a function. All right. So that's how you apply your vertical line test if you are asked to identify if a diagram is a function or not. Okay. Okie dokes. Let's see now what our notation is all about. Okay. What we've said over here is that because functions are special relations, we give them special notations. We refer to them in special ways, okay? And essentially, the one way is your mapping notation, and the other is your functional notation, all right? Now, remember, the concept of a functional relation is that we've got x values, which we subbed into an equation, and out came y values, okay? So your y values are very dependent on what went into your equation as x values. I'm sure you guys all agree with that. It depends on what went in as an x that came out as a y. So what we say over here, mapping notation. Let's just have a look over here. This is our mapping notation, and this is what it looks like, guys. We've got f semicolon x is mapped onto, and we show that just by a little arrow, to 2x. So as you can see what it says here, this reads f maps x onto 2x, all right? So if x is equal to 3 is an element of the domain, remember your x values are your domain, all right? Then the element of the range, remember the range is the y values that came out, is going to be 2 times 3. Remember that obviously the 3 had to get substituted into the x. And obviously what we get there is 6. So we say that 6 is the image of 3 in the mapping of that relation. Okay, so putting a long story short, when we put 3 into that equation, what came out as the dependent y value that's part of the range, is then 6. Okay, so that's your mapping notation. It's just a way of showing functions. Okay. And your functional notation, another way, a very common way, guys, of showing showing functions. Okay, probably slightly more common than your mapping notation, is your functional notation. All right, functional notation is going to look like this. We say f of x, and we show it inside a bracket, and we read it f of x is equal to 3x. Okay, sorry, that should actually be 3x over there then. So f of x is equal to 3x. All right, so that means that f of x represents the value that's going to come out when I substitute an x value into my equation, all right? So something that you must be quite clear on is that you understand that, in fact, this f of x over here is really talking about the y value that comes out when we substitute an x value in, okay? So f of x means the value for y that came out according to whatever x value went into the equation. I hope that makes sense to you guys. Okay, Looney, does that make sense to you?
Of course.
Okay, right, let's have a look then and see what we've got in terms of this notation over here. Just to get you guys familiar with it, let's take an example. We've said that f of x, okay, now remember that's just another way of saying y. We're talking about y there when I refer to f of x, okay? F of x is equal to 2x squared minus x plus 1. All right, so this is what they're asking us to do. They said determine f of 2. All right, so let's think about this for a second. F of 2 means I want to know what is the y value when my x value is 2. All right? So in order to do that, what I'm going to have to do is take my equation, and everywhere where we've got an x, we are going to have to substitute it with what we've got inside this bracket over here, which is 2. All right. So once we've done that, we'll then actually just work it out. So that's going to be 4 times 2, which is 8. I've got minus 2, and I've got plus 1. And that's going to give us 7. Okay. So therefore, according to this function, according to this relational rule over there, when I've got an x value of 6, and I plugged it into the equation, out came a y value of 7. Okay. And if we took a whole lot of values for x and we substituted it into that particular equation, because that's a special type of equation, it's always going to give us back a particular type of graph, okay? As would it do if I had a linear equation or a hyperbola equation, okay? All right, so just to make it a little bit more algebraic, what if I was saying f of a? All right, so again, what that's saying is that in terms of a, what would the y value be if my x value was a? Now, they can do this to you, okay? It doesn't have to be numbers. I'm sure by now you know in maths, we love to throw letters in there. It doesn't have to be numbers. So in terms of a, which is saying your answer is going to have a in it, but what would the y value be if the x value was a? All right? Exactly the same process happens. We substitute a into every place where you had an x, and out comes the y value. So we're now substituting a in there and a in there, which gives us, I'm just going to have to write it on the side here because of space, it's going to give me 2a squared minus a plus 1. Now, it doesn't look very neat and tidy, I agree with you, but that's the y value that comes out where the x value was a. All right. Right, one more thing to do with notation. What are they asking me for here, grade 10s, if I've got f of x is equal to 4? All right, so what are they asking me for? Remember, the thing to relate to is what is the value, what is f of x? All right, now remember f of x is actually the y value. All right, so this time we're asking it in reverse. We're saying, well, if the y value was 4, what's the x value that's related to it? Would I do it exactly the same way as I did where I had x's? Absolutely, except this time I'm going to substitute 4 into the place of your f of x. Okay, so our f of x equation was 2x squared minus x plus 1. That was our equation. And we've now said that f of x is actually the value of 4. All right, so if I sub in that in there, do you agree what we've got is an equation which is actually a quadratic equation to solve for x? So we're going to bring my 4 over, and negative 4 plus 1 is going to give us negative 3. Okay, this is just a good old quadratic equation which we need to solve. All right, so we're going to have a 2x and an x. That would have to be 3 there, and that would have to be 1 there, and we'd have to have a minus and a plus. Okay, so x is equal to 3 over 2, and x is equal to negative 1. All right. Back in our key concepts, I mentioned an equation that looks like this. We've got y, which is equal to a multiplied by x minus x1 multiplied by x minus x2. Okay? The x1 represents your first x-intercept, and the second represents your second x-intercept. So in order to find the equation of this parabola, what I'm going to do is substitute my negative 4 into my x1 and my positive 4 into my x2. Okay? So therefore, this is what we will then have. I've got y, which is equal to a, x. Now, if I substitute negative 4, that means I've got 2 negatives, which is going to become positive, and x minus 4 over there. Okay, that's all fine, but I still have too many variables. It's a problem. We need to get rid of some variables here. And what we're going to notice is that I've got a coordinate point over there. I've got the point of negative 1 and 15. And remember with the graph, the best thing about graphs is that if in doubt, if you've got a point that is sitting on your line, guys, you are always allowed to sub it in. Okay, so x is negative 1, y is 15, and that's exactly what I'm going to do. I'm substituting everywhere I see an x with a negative 1, and everywhere I see a y, and everywhere I see a y with a 15. Okay, so that's what we've got over there. And that's leaving me with just one variable to solve for, which is my a. So therefore I've got a 5, I have got, no, so that should be 3. Hey? Okay, let's just make sure we get those right. Okay, so we should have 3, and we should have negative 5, which is going to give us negative 15, which if I divide positive 15 by negative 15, we get negative 1. Guys, looking at your graph, should the a be a negative? Okay, should we confirm that? Let's have a look. Absolutely, it's a frowning graph. So yes, it should be negative. So what have we got in terms of our equation? I've got y is equal to, instead of a, I've got a negative 1, and I've got an x minus 4, and I've got an x plus 4, which we're now going to just multiply out, okay? That's going to give us x squared minus 16, and if I distribute my negative, I'm going to land up with negative x squared plus 16. And what is that plus 16 again? Let's go back to our graph. That would represent the y-intercept, or the turning point, or the maximum value of your graph. So it's got lots of different characteristics at one little point over there. Okay, right. That's the parabola. Okay, you guys need to go and practice it, go and draw lots of them, go and practice finding the equation of them. They are very important graphs to understand. Okay, right, guys, let's have a quick look at exponential functions. Yes.
Before you move on to that, I have 2 questions based on the domain. The first one is from Bradley saying, can you please explain again what you mean by the domain? But another specific one is from Gumani. It says, when writing the domain, is it okay if I write x is an element of a real number?
Absolutely. In fact, that's a very good question. Instead of writing from negative to positive infinity, another way of writing it, it means, and neither one is correct or incorrect, it's just another way of writing it, is to say x is an element of any real number, which it is, because you're covering everything from negative to positive infinity. Regarding the domain and range, I'm going to suggest something. On our notes from last week, which I think are still on the website,
Yes.
go and have a look at those notes regarding domain and range. We covered it quite extensively there, and just go have a look at it, but I'll try and incorporate it into the exponential graphs just so we can help you understand that as well. Okay, so we can kill two birds with one stone there.
Yes, I'll make sure that I post the
Perfect,
notes.
that's great, super. Okay, the exponential function, let's just quickly look at our standard equation. Y equals ab to the power of x plus q. Okay, what we need to understand about our exponential graph, all right, is that this over here is our standard shape. That's what our standard exponential graph is going to look like, okay? The a, what does the a do in our graph? This a determines whether your function is a positive or a negative function. If it's positive, your function will always be on the positive side, on the positive y-axis. So it's always going to be on the upper half of your Cartesian plane. If your a is negative, it is always going to be on the lower half of your Cartesian plane. So that's what you need to always be aware of with regards to your a value. And your q value is going to determine the y asymptote. Okay, remember we said the asymptote is a line that your graph gets closer and closer to, but it never actually touches it, it never crosses it, okay? So if my y in asymptote is greater than 0, we can all see this dotted line over here. This over here represents the asymptote. And my exponential graph will get close to it, but it never ever crosses. Whereas if my y asymptote was less than 0, so in other words it's lower than 0, so it would be below the x-axis, but again, you can see that the the exponential graph will never ever cross it. Okay, so watch out for your asymptote. It's a really important part of your exponential graph. It determines how high the domain, well, not the domain actually, it determines the range of your exponential graph. It really does. Okay, so let's have a look at an example quickly, and let's see if we can just quickly draw this so you guys are all happy and understanding. Right. What have we got here? I've got a 2 to the power of x minus 2, okay? The first thing I think is important to note is always note what your asymptote is and draw that onto your axes, okay? Just sketch that in because you know that that's a really important part of your graph. So I'm going to take a dotted line, let's just use a green one, and I'm going to do a dotted line through the point of y equals negative 2. Always make sure that you label your asymptote. Okay, so give the line an equation, and this one is y equals negative 2. All right. Now we need to plot the graph. Your best bet, guys, is to do it by means of a table. Okay, so give yourself a table with x values and y values, and you can substitute in. The other option, remember last week I showed you how to plot it with a calculator, and let me show you again. We press mode and we press 3 for table. That brings up our equation, which we are going to type in. No, we want it as an exponent. Minus 2. It asks us where we want to start. I'm going to tell it at -5 and to end at -5, going up in steps of 1. Right, and it gives us all the points that we need to plot, the x and the y coordinates all the way along it, okay? Right, I'm not going to spend too much time plotting it too accurately purely because of time constraints, so I'm going to just draw the graph, okay? The one point, in fact, that I am interested in is what is the x-intercept? And the x-intercept is going to be where the y is equal to 0. Do we have a y equals 0 here? Okay, let's see. Okay. All right, let's find points that we can plot here. Where x is 1, y is 0.5. Where x is 1, y is 0.5. That's a point we can plot. Let's see what we've got here. Where x is 1, 2, y is 1. Okay. All right, so sorry guys, because of time, I'm not going to be able to plot this too carefully, but let's just give you an idea. So essentially your graph is going to go like this. It's going to go through here. It's going to pass through your x-axis at a particular point. It's going to get closer and closer to the asymptote. but it will never cross it. And in fact, it takes a more regular, it has a more regular curve than what my picture actually looks like over there. So what's important when you're sketching your exponential graphs, make sure if you've got a positive value as the coefficient of the first term is positive, the graph is on the upper half of your asymptote. The asymptote itself, make sure that that's always a dotted line passing through your y-axis. Label your asymptote. That's a really important mark that I don't want you to lose in your plotting of your graphs. And then make sure that you've plotted. When you're plotting it, guys, you don't need to be ultra specific about it, because it does get very, very small. It gets ridiculously small. So the point is, you're wanting a relatively close representation of your graph. Draw a few points, plot a few points, but you don't need to be too serious about the 0.00067 value, okay? Those you don't have to worry about too much. Use your calculator. Practice that method of actually plotting points on your calculator. It is extremely handy. And that same method can be used for your hyperbola, as well as the parabola and the straight line graph. So you've got to now actually establish a method or means of sketching these graphs that works for you. You have a few methods available to you, and as long as you are correctly labeling your graphs, correctly filling in coordinate points such as x and y intercepts and turning points and so on, as long as you are filling in all of that essential information on your graph, you will get the marks that you need. Okay. Guys, I hope that that gives you a good introduction to your functions and that everyone's
One last question, Tamlin. From Timosho quickly. It says, I don't understand with determine increasing and decreasing x values.
The x values, once again, I can give you a very quick, let me try this on the graph over here. I'm going to black it out for a second, and I'm going to pull it across. Okay, look what I'm doing over here. I'm pulling the shade of the screen horizontally along the screen like so, okay? And that's what you're doing. You're going horizontally across the screen. And as you're doing it, look what's happening to the purple line. It's getting higher, and it's getting higher, and it's getting higher as I'm going along my x values, okay? So for which values of x would this graph be increasing? Well, it's going to be all the values for x. As I go along, the whole way along my graph was increasing. So to answer that question, using this as an example, the values for x for which your graph would be increasing is that it would be an element of any real number, because your graph increases all the way along. And that's what you need to do, guys. You need to look horizontally across your x-axis.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. We have got such exciting news for you. From July, a new program starts on Mindset just for you. It's called Connections. We'll chat about the issues that affect your life, your school, and your relationships. We'll have fun, take your calls, and have great prizes up for grabs. Connections from the 1st of July, 7:30 in the evening, only on Mindset. For you, by you. Welcome back from the break. I know you can't wait for the term to end and the July holidays to start. And of course, that means winter school. This year, we will be repeating all the Term 2 Learn Extra live shows for you from the 24th till the 28th of June from 9 a.m. in the morning till 7 p.m. at night. So don't miss out. Go to our website www.mindset.co.za/learn/extra/winter school to get all the details and to download the notes for each lesson. But for now, let's get back to today's revision lesson. Over to you.
There are many different ways in which we can go about drawing a straight line graph. We can either plot a table. All right, you've got values for x, you sub the values for x into your equation, and we get the values for y. All right. There's another method called the dual intercept method, where I work out the x-intercept and I work out the y-intercept, and we plot. Or we could even use our calculators. Can you believe it? Okay. So what I'm going to do, guys, is show you each of the methods very quickly so you can decide which of the ones you wish to use. Okay. Right, table method is going to go something like this. We're going to have ourselves a table where we're going to have a couple of blocks in it, and we've got values for x and values for y. I'd give myself a couple of values to work with. You don't need to go too far, though. It's not necessary. And what we do is we take each value and we sub it into the equation. So the first one would be negative 2 times by x. Let me just take that out. It's not negative 2, sorry. Positive 2 is the equation. So positive 2 times by x, which is negative 2 plus 4. Right, so that's giving me negative 4 plus 4, so there I've got 0. If I substitute negative 1 into my values for x, that's giving me negative 2 plus 4, which is giving me positive 2. So that was 0, that was 2. If I substitute 0 into the equation, I'm going to land up with just 4. If we put 1 into the equation, that's going to give me 2 plus 4, which is 6. And finally, if I put 2 into the equation, that's going to give me 8. Okay. All right, so that's fine. It gives me the values that I need, but I'm sure you agree it's a little bit untidy and it requires quite a bit of working out. So I would suggest to you that if you've stuck on it, use your table method. Otherwise, if you're needing to push yourself with time, try not using the table method. Let's see if you can get an understanding of this next method over here. I'm going to do it in a different color. This over here we're going to call the dual intercept method. Okay, dual intercept, basically we are working out the y-intercept and we are going to work out the x-intercept. Remember, that's where the line cuts the x-axis and where it cuts the y-axis. And the way we work out the y-intercept is we say, let x equal 0. And to work out the x-intercept, we say, let y equal 0. So therefore, if I've got my equation, I'm going to say y is equal to 2 times 0 plus 4, which is going to give us just 4. And y, we're going to make y 0, so let's just take that out. Okay, we want y to be 0. And that's equal to 2x minus plus 4. So therefore, I would land up with negative 2x is equal to 4. So x would be equal to negative 2. Okay, so let's plot this now. Let's draw ourselves an x and a y axis. I'm going to do it over here. And let's plot our points. Okay, we had 1, 2, 3, 4, 5. And in fact, we went a bit further on. So I'm just going to go all the way up to 8 over there. Okay, so sorry, I had to miss out 7, but not too serious. Negative 2, negative 3. Right, we've got 1, 2, 3, 4, 5, 6, 7, and 8. And, oh, no, negative 1. Negative 1, 2, 3, and I think we are going to be okay with that. All right, so let's use our table first. Let's plot the points that we had. So the first one I had was negative 2 and 0. So my x is negative 2. My y is 0, which means we are sitting over there. That's my point. The next point we had was negative 1 and 2. So x is negative 1, y is positive 2. That's going to give us that point over there. The next line that we have, next point I have is 0 and 4. So x is 0 and y is 4. That is going to give us this point over here. And I've got 1 and 6, where x is 1, y is 6. X is 1, y is 6. And finally, where x was 2, y was 8. So, can you see that we've landed up with a line that is a straight line? And that's no coincidence, guys. I knew it was going to be a straight line graph. And how did we know that? Because if we go back to our original equation, did it form or did it fall into the standard equation of y equals ax plus q? Yes, it did. The a was 2, the q was 4. Let's test something quickly. Remember we said the a represented your gradient, and if your gradient was positive, it was a climbing graph, right? Let's check ourselves. Is that a climbing gradient? Yes, it is. Okay, so we've got a positive a value, and the q was positive 4. And remember, that was where your line was crossing the y-axis. Now, positive 4, yep, that's exactly where it's crossing your y-axis. So that is your straight line graph. All right, now, just to bring in this point over here. If you didn't use the table method and you used the dual intercept method, you landed up with two values. You had x was equal to -2, and you had y was equal to 4. Now, if you just had those 2 points there, we would plot that y would be equal to 4, and x would be equal to -2. And if I were to draw that line, let's just choose a different color. If I were to draw that line, do you guys agree it would be exactly the same line? So whether you use the table method or whether you use the dual intercept method, you are going to get the same line. Okay, so you need to play with it. You need to work with the method that suits you. Okay, and that really is the case. One more method is using your calculator. Okay, so let's show you how that's going to work. All right. I hope you've got your calculators with you, and just work with me as I'm doing it. Follow the buttons that we're pressing, and this can be used to sketch not just linear, any of your graphs. Okay, so let's have a look here. The way we do it is this. We take mode, we press mode, and then I have to press 3 for table, okay, and we bring up an f of x equals, which now we recognize is our functional notation. Remember, f of x represents the y value that is connected to the x value that we're subbing in, okay. So what was our equation? It was 2x. Now on the calculator, the way we get x is we press alpha, and then we press this button over there. Can we see that that gives us an x? So we had 2x plus 4. All right. So once you've typed your equation in, all right, then what you do is you press equals, all right? And your calculator asks you start. It's asking you, where must I start, okay? It's suggesting that you start at 1, but we're going to suggest you start a little bit further back than that. So let's start at -3, all right? It's just giving us a few values on the negative side, which will give us a bit more space to work with. Once we've set that, we press equals. And the calculator says, where must I end? All right? Well, I started at -3, so let's make it the same on the other side. Let's end at +3, okay? And press equals again. It says, what steps must I go in? Must I go in steps of 1 or 2, or how must it go? So it's asking, should it go in steps of 1? And you're going to say, yes, we want it in steps of 1. So we just press equals. And what comes up is a table of all your coordinate points. Okay, so I hope you guys can see this on the screen. I know that it sometimes looks a bit small, but if you can't, sit with your calculator and work with it, because you might find this a bit handy. Okay, and essentially this column over here is showing us the x values, and the one next to it is the y value that's connected to it, and each of those form the coordinate points that you're going to plot. Okay, so again, go play with that. See if it works for you, because it's also a nice handy way of checking, if nothing else, that your line is correct. Okay, guys. So that is how we sketch a straight line graph. Right, looking at this equation over here, I've got x plus 2y equals 6. My question is that a linear function? How do we know? All right. Now, with a function, the standard equation of a linear function, remember, was y equals ax plus q. So can you guys quite clearly see that y is on its own? Y is isolated on its own on the left-hand side of the equation. Now, the problem with the way we've got it over here is that y is not on its own, and that we don't want it like that. So we need to rearrange our formula, and we need to get it into the standard form of ax plus q. All right? So what does that mean? We need to get y on its own. So that's what I want to get on its own. So the first thing that needs to move is my x. All right? So we are going to say that 2y is equal to -x plus 6. And then to get y completely on its own, we need to divide it by 2. And everything gets divided by 2, meaning I've got -x over 2 plus, and that will become 3. So, is it a linear function? Well, if we look at it, I've got y equals ax. My a in this equation actually works out to be -0.5, and the q in my equation works out to be +3. All right? So, because my a is negative, is my gradient a climbing gradient, or is it a sliding gradient? I'm sure you guys are saying to me, it's sliding. Okay, so it's going to be just roughly, it's going to be a negative gradient. It's going to face that direction over there. What is this telling us? It means that I've got a y-intercept at positive 3. All right, how are we going to plot it? You've got all these different methods that you can choose from. I want you to use the method you are comfortable with. The one that I'm going to use is the dual intercept. I'm going to work out the x-intercept and the y-intercept and plot them. Okay, so we're going to have my x and my y-axis. All right, we should always label them correctly. So I've got my x and my y-axis. Right, if I let's do the working out at the bottom here. If I let x equal 0, remember, that's working out your y-intercept. So I would say y is equal to negative 0 over 2 plus 3. And in fact, that gives us something we already knew. We knew the y-intercept was 3. And let y equals 0 means I'm going to land up with 0, which is equal to negative x over 2 plus 3. All right, let's bring our 3 over. So we're going to land up with negative 3 equals negative x over 2. Instead of dividing by 2 on the one side, I'm going to times it by 2 on the other side. So we get negative 6 equals negative x. And if I divide by negative on both sides, we get positive. So I get x is 6 and y is 3. So my x value is going to be a 6, and my y value is going to be a 3. And from there, we can plot our line. Double check this for me, guys. Is this, let's just put it there, is that the negative gradient that we knew it was going to be? And I think we all agree that that's a negative gradient, so we're happy with that. And does the line pass the y-axis at positive 3? Yes, it does. Okay. So my gradient was negative, and my y-intercept was 3. Okay. So that's how we work with a linear function. All right. Very quickly, we're going to have a look, guys, at some hyperbolas, just so we're skipping through a few things over here. In fact, let's not rush it. We'll have a look at some other things quickly here. All right, before we go into hyperbolas, let's finish off our linears properly. If you have got, I want you to take a careful look at these two equations over here. I've got y is equal to negative x plus 3, and I've got y is equal to negative x minus 2. All right. What I'm going to suggest you do, I'm still going to make you do some work before the end of the lesson. Sketch those quickly. All right. I want you to sketch them on the same graph, and I want you to plot them neatly and carefully. And once you've plotted them on the same set of axes, I want you to tell me what you notice about those two graphs. Okay, so Looney's waiting for you to let her know. Plot them. I want you to tell me, what do you notice about those two graphs over there when you plot them? There's something special about them. Okay, all right, get that done quickly, guys. And while you're doing that, I'm going to talk about finding the equation of a straight line graph. Okay. It's all very well if they give us the equation and they want us to draw the graph, but it can work the other way around as well, where they give us the graph and then obviously we have to give them the equation. It happens, and they definitely require us to know how to do that. So where do we start? With any graph. If you are having to find the equation of the function that's been given to you, guys, start with the standard equation. Okay, that's your starting point. So because this is a straight line graph, I'm going to start with the standard function or standard equation of ax plus q. All right? Now, the a we're going to work out is our gradient, and the q we know is our y-intercept. Now we've got to very carefully look at our graph and see, well, what information have they given me over here? So what they have quite clearly told me is that I've got a y-intercept of positive 3. Okay, so I know, or we should know, that that then goes into our q, because that's the y-intercept. So let's substitute that in. So I've got y is equal to ax plus 3. And then they've given us this point, which is kind of sitting in the middle of nowhere, but we know that it's where an x value is 8 and the y value is negative 1. So we've got this coordinate pair which we can work with. And the nice thing about functions is that if you've got a coordinate pair, or if you've got an x value and you need to know what the y value is, we sub it into the equation. Okay? So into my equation, Where I've got an x, I'm going to substitute 8. And where I've got a y, I'm going to substitute -1. Okay? And I'm sure we can all quite clearly see that the value we're actually looking to now solve for is your a, which is your gradient. Okay, so we're going to land up with -4/8, which is equal to a. That's going to simplify to -1/2. Right, let's double check ourselves. This a is negative, which means my gradient is sliding down the hill. If we check ourselves, yes, that gradient is negative, so we write in that. And the other thing, remember, is that the y-intercept was 3, and if we look at our equation, the y-intercept is 3. So the equation of my graph is y equals -1/2 x plus 3. Okay. Right, so there we go. So you've got to look at the information that's been given to you. You have to start with the standard equation, all right? And you substitute in what you know, and you will get there. It's actually quite easy to do. Has anybody come up with the answers to that previous question?
I think Apiwe has, because he says it's a sliding gradient, which means it's got a negative slope.
Okay, he is right with that, but did he mention anything else?
No.
Okay, this is what I want you to notice, guys. If you've plotted it, all right, and I'm going to run out of time, so I'm not going to do all the plotting, but I'll tell you what you're looking for. Do you notice that the gradient in my first equation, which is negative, so you're absolutely right, it's sliding, and the gradient over here are the same. They've both got an a value, which is -1. Okay? Now, this is what we know. If they've both got the same gradient, then what's going to happen is that when we plot them, let's use a straight line so we don't do it badly. When we plot them, if they've got the same gradient, it means that the lines are going to be parallel. Okay, and that becomes a really important concept to know. So any two straight line graphs that have got the same gradient will always be parallel, in which case they run equidistant to each other. All right, so I'm sure some of you guys got that over there, but if you didn't, carry on with the sum, sketch the two equations, and actually test that. Work that out for yourself. And just to make a note that the same gradients give you parallel lines. Okay. Parallel lines. All right, guys. Okay, unfortunately, we're going to have to leave our hyperbolas to next week, but I'm going to be back next week, Monday, and we're going to go through our hyperbolas with you. The hyperbolas, the good news is they're actually really easy. They're not difficult graphs to plot, so we're going to go through those quickly before we go on to our quadratic and our exponential equations. Big section, guys, lots of work to learn, and if you understand the basics, I'm sure those of you in grade 11 and 12 can verify, if you understand the basics, it's not a difficult section. You just got to practice it. That's the thing. You've really got to spend time working on it.
Now it's time for a break, so don't go away. We'll be right back. Welcome back, Mindsetters. In case you missed my news, starting in July, we have a new program that is going to get you talking. What's on your mind? What are the issues you deal with? How can we help you? Connections will help you with all that and more, so make sure you catch it. For a fun and youthful look at life, connect with us on Connections. But right now, let's do some more revision.
We're now going to have a look at a Trigraph question. Now, the question says, sketch on the same system of axes, f of x equal to 2 sine x, and g of x equal to cos of x plus 1. Now, guys, firstly, this question isn't really complete because the sine graph and the cos graph will carry on forever unless I restrict the domain, right? So either I needed to give you guys a number line that finished at 360, or I needed to say something like 4x an element of 0 to 360 degrees. Right. So this, what we give you, the x is an element of 0 to 360 degrees, that's the domain, okay? In this case, our domain and our period is going to be the same, but if I ask you to sketch the graph up to 720 degrees, even if you draw up to 720 degrees, in other words, you fit in two graphs, your period is still 360 degrees. Your domain is whatever we tell you to sketch the graph for. Okay. So very, very important is I need to have an idea in my head of what I'm working with. So if I look at f of x equal to 2 sine x, I see that that 2, which comes in front of the sine, is the a, and the a affects the amplitude. So unlike the ordinary sine graph that has a maximum value of 1 and a minimum value of -1, this graph is going to have an amplitude of 2. So that's where I'm going to start. And I'm going to put in all my relevant points, 0, 90 degrees. I'm trying to keep them evenly spaced, 180 degrees, 270 degrees, not that evenly spaced in the end, and finally 360. So I'm going to put on my y-axis 1, and I'm going to put on 2, because I know that it's going to go all the way up to 2, and then on my x-axis -1. Sorry, on my negative y-axis rather, and -2. Okay, now this is a sine graph. I know that it reaches its maximum value over there at 90 degrees. Guys, try and keep it nice and curved. I know it's not always easy. And it's going to go down there to 180. It's going to go down to its minimum value over there at 270. And up to 360. And it's never a bad idea just to indicate with a little dotted line that that is on par with 2, and this is on par with -2. Now, I know my graph's not beautifully symmetric, but that's a pretty good effort. All right. Now I need to talk about my cos graph. The cos graph is y is equal to cos x plus 1. Now, the cos graph's amplitude is still 1 because the value in front of the cos is 1. However, what has happened to the cos graph is that it has been vertically shifted up by 1 unit. So I want you guys to visualize my cos graph that has shifted up 1 unit. I'm going to go back to these guys over here, and I'm going to say y is equal to cos x plus 1. So guys, this is what I'm looking at. What's going to happen is my cos graph is going to start at 2. It's going to gradually go down. It's going to reach its minimum value over there at 180, and it's going to go up to 2 again. But it's important that the amplitude of the graph is not 2. The position of rest is still in the middle here, and the maximum displacement from the position of rest is still only 1 unit. So let me quickly draw my cos graph. Now, guys, this is a little bit easier said than done, especially, okay, let's just try a different color at least. It's going to go gradually down there to 180 and all the way back up to 2 over there. Right, guys, that definitely isn't the prettiest graph, but we have shown you guys exactly what it looks like with the electronic software.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to join us for winter school from the 27th till the 30th of June, when we will be repeating all the Learn Extra live shows from Term 2. We'll be back with live shows from the 15th of July for Term 3 lessons.